Okay. Maybe we can start in 2 minutes.
Yeah.
Yeah, let people join.
Right.
I see 20 people have joined.
That's already a good number.
Yeah. No, we have like good registration,
Yeah.
right?
Yeah.
100 plus, right? Is it?
Oh, yeah,
181.
or 200 almost, yeah.
Yeah.
Oh, wow.
Yeah, just give like, 1 or 2 more minutes because I'm sure, people are just joining. Especially in
Yeah.
US, I'm sure people just waking up and
Yeah,
joining.
that's right. It's too early.
Yeah. The screen is now
Yes.
showing the IISA, the blue screen, right? Yeah.
Yeah,
Okay.
yeah, yeah. But you can move, right?
Right. That's what I'm testing. I can move it, but I'm seeing another screen, so I just make sure that I'm sharing the correct screen.
I can see
Okay.
the blue screen with
Yeah.
IIS.
Yeah.
But I am seeing only my screen.
Oh.
Should I maybe stop share then, or
Yeah. Maybe that I.
maybe I stop share then? Okay.
Mm.
Okay. Mm, But I'm not seeing, I'm just seeing you guys, I'm not seeing the screen,
Oh.
your screen.
Oh,
Why it is so? You can in the
So actually,
view.
Zoom now has multiple tabs. So if you see, there is a tab called webinar, another called Kaushik screen. Can you see the two tabs on the top?
Okay. Webinar and Kaushik
Yeah.
screen. Okay. I see. Okay. Kaushik screen. I see. Okay.
all right. I think it's 8.
Just to wait for a second. Hmm. Just just wait for a second. Maybe the same problem I'm facing now. Yeah. Webinar and share screen. Where is my? I also can't see this. Oh, right. If I yeah. Okay.
I can see your screen.
Yeah, but I can't see. I see it, but it's small one. Why it is small?
Kaushik, I think I can just start.
Yeah, but you can change the
Yeah.
slide.
No, I cannot. Can you
That's
help me
yeah.
to, if I say next slide, can you go to the next slide?
That's what I'm trying. Is it changing? No, not changing, right?
No.
Okay, let me stop share and then again. Share.
Okay, I can see your screen.
Okay. So,
Oh, you have to do
yes.
enable editing. Yeah.
Yeah. Go ahead. Yeah. Now I can change
Yeah,
my
I think
screen.
we should start.
Yeah.
Yeah.
Yeah. Please
Eight,
start.
8 or 2.
Hmm.
Yeah. So first of all, thank you everyone for joining today's webinar, because today's webinar is also very special for IISA. We are going to talk about like who is today's presenter, and you will see, how it is special and also the topic as well. But my name is Iya Banerjee. I'm the currently president at the International Indian Statistical Association. I know many of you probably heard about this association, but many of you probably don't know. So this is like, an association primarily. I mean, it is for everyone, but it was primarily meant for the Indian subcontinent statisticians. Anywhere on this world. Kaushik, if you go to the next slide. Yeah, so our objective is we're promoting education, research, and application of statistics and probability throughout the world with a special emphasis of Indian subcontinent. We obviously foster collaboration for development of statistical science, and we are always fostering the young statisticians. Besides that, we are encouraging any cooperative effort among the members, in education, industry, government, and business. Can you go to the next slide? So for IISA, we do annual conference every year, which is our flagship event. And in 2025, the annual conference is going to happen between June 12th to June 15th. So I would like to take this opportunity to invite all of you who are on the call to come to University of Nebraska at Lincoln. And the registration will open on March 1st, 2025. This is in 2024, we had just the annual conference in December in India. So one year we do conference in India, and another year we do the conference in US. And I can guarantee you will learn almost every aspect of the statistics in this type of conferences. And or another thing I want to mention, we do have a student paper and poster competition, which is very prestigious. And so I want to emphasize to the people who are online, if you have student, please encourage them. Or if you are a student at this moment, please apply for all this paper and the poster competition. And we are going to start abstract submission, in sometimes in February, but the submission deadline is on April 1st. We go to the next slide. For the website, I will update you sometimes on our LinkedIn page. So one thing I want to emphasize, because as I just mentioned, this community want to foster the young statisticians. So that's why we take student paper and poster competition seriously. It held every year during the annual conference, and it has two category. One is a theory and probability category, and another is an application category. And there are multiple awards. There is no fixed award at this moment, but yeah, we give multiple awards during every annual conferences. If you go to the next slide. And we also have early career award, which is also very prestigious award. And Bibhas, if I'm not wrong, you got one time. So it's three category: theory, application, and the interdisciplinary studies and practices. So that's why anybody who is studying or who is working in any statistical work, and doesn't matter which area, you can apply. If you go to the next slide. I just want to emphasize the membership, obviously, it's a 501c organization. We do depend on my membership, the life membership from anywhere, around the developed country. I put here US, but it can be UK and other European countries as well. It's $450 for lifetime, and the annual membership is $50. But if you're from India or any developing country, the annual membership is $7, and the life membership is $60. But I also want to emphasize the student membership is free for 4 years, but you have to give either a student ID or some sort of proof that you are a student. And please take this opportunity to become a member and to make a change in the organization, which is beloved by all of us. Any other slides?
No, yeah, it's the last slide.
So,
yeah.
So saying that, I want to welcome everyone in this webinar. Thanks a lot. And I'm going to hand it over to the today's moderator, Kaushik Chana, who is a professor at Indian Statistical Institute. Thank you, Kaushik.
Yeah, thank you, Dr. Banerjee. Yeah, hello, everyone. Good evening, good afternoon, good morning, based on where you are located now. It is an absolute honor for me to introduce today's speaker, Professor Bibhas Chakraborty. And he's going to talk on reinforcement learning algorithms in mobile health trials, which is very important and hot topic nowadays. And and we'll get to know more about this in the lecture. But before that, I'm going to give a brief description about his work and affiliation. So he is a tenured associate professor and director of the Center for Quantitative Medicine at the Duke University and National University of Singapore Medical School, Duke-NUS. And before that, he was a tenure track assistant professor at biostatistics at Columbia University. He is a recipient of the Calderoni Research Prize from the Columbia University in 2011, and we are also very delighted that he is also one of the awardee of Young Statistical Scientist awardee from today's host in International Indian Statistical Association in 2017. He is an elected member of the International Statistical Institute. He authored first textbook on dynamic treatment regimes. I hope he will tell more about this in his lecture also. And but before I hand over to the speaker, I would like to announce two important points, the housekeeping kind of announcement. We are recording this webinar, which we will upload in our YouTube channel, in IISA YouTube channel for viewing later. And also we will take question answer at the end of the lecture, but feel free to kind of post your question in the chat bottom available in your Zoom screen. We will take up those questions, and if time permits, we'll request you to unmute and ask your question. So with this, I invite Professor Chakraborty to share this interesting research with us.
Thank you, Dr. Jana, for the kind introduction. Can you hear me all right?
Yes, it's
yes. Okay, good.
Yeah.
All right, so I'll start with some words of gratitude. So not just Kaushik, but to Himel, Hia, Jyotishko, Piali, everyone in the committee of this webinar for the kind invitation, and also to you all, this community, which is giving me this platform to share my work. I would also take the opportunity to acknowledge the funding that I have received from Duke-NUS Medical School, my employer, and the Ministry of Education, Singapore, through national grants. So before I go to the actual topic, I thought it would be good to showcase these two books that I have worked on. And as you see, as Kaushik mentioned earlier, the first one is on dynamic treatment regimes. And the second one is even broader. It's on precision medicine. I've been working in these areas for a long time, since my PhD days. But while this is a specific application area, in the back end, there has always been this confluence of reinforcement learning and causal inference, to some extent, adaptive clinical trial designs. And these backbones, they kind of got repackaged again in this newer area called mobile health, in a slightly different way, of course, but fundamentals are kind of connected. So with this background, I'll move to the mobile health part, which is the topic of today's talk. So as you know, mobile phones are everywhere, and that creates a tremendous opportunity to reach very far away corners of the population, and that can help reduce disparities. I mean, we can keep on talking about the social or global health aspects of this, but today's talk is not about that. So I'll move on quickly to the more statistical aspects. I just wanted to highlight some of the bigger pictures very briefly. So mobile health, or in short, it's called mHealth. This is utilizing this mobile or wearable devices to all these technologies to improve health and wellness. And Eric Topol, who is a famous so-called precision medicine guru, predicted correctly a number of years back that the smartphone will become the hub of a new era of personalized medicine, transforming the way we monitor and manage our health. And that's what we are seeing in many places in today's world. Now, mobile health can mean a variety of things to different people, but I will be primarily, almost exclusively focusing here on the aspect of mobile health that deals with messages or push notifications or nudges on mobile phones. Sometimes these are called just-in-time adaptive interventions, or JITIs. And they can be applicable in a variety of settings, different disease areas, different behavior change, like smoking cessation, alcohol reduction, physical activity promotion, and so on. So in this context, there is a new kind of trial design. I'm sure everyone here knows about the classical randomized controlled trial that is used in clinical trials, but these are slightly more than that, and I'll come to that. These are tailor-made for these just-in-time adaptive interventions. And it was first introduced in 2015, so you can realize it's very recent. And they can potentially take care of multi-component, time-varying, and sequential nature of the interventions, because this is behavior change we are talking about. So we have to keep giving these nudges again and again and again. So intervention is not a static thing. Intervention has to be ongoing. And here, the main idea is that each person is randomized between possible intervention options at many, many stages. And it could be in the order of hundreds or even some cases thousands, depending on how long you are doing it. It can be a nudge every day. It can be nudges every few hours. There are a variety of examples. And because at every stage, you can have more than one potential factors of the intervention, and you will see examples as we go along the talk. So this can be, at every stage, it can be a factorial design. Again, because this is a statistical audience, I assume that most people are familiar with that. This is like those who have studied statistics in undergrads, it's a standard thing in undergrad curriculums. So it's a factorial design, more than one factor.
Yes.
Hi, Bibhas.
Yeah, sorry, I got disconnected.
Yeah.
Disconnected.
Yeah.
My screen is up or no? Screen is not up? No, right?
Screen is not up, right?
Not up, okay.
Yeah, we just lost for 10 seconds, 8, 10, 15 seconds.
Oh, okay. Is it up now? No.
Not yet, no.
Not yet. Okay. Give me a minute, okay? It should be up now. Yeah. Okay. All right. So I was just talking about the micro-randomized trial design, which is a sequential full factorial. I think I explained that. And now the different factors, different intervention components, they are intended to have proximal effects in this situation. This is another thing to understand here, to take note. So for example, I send these nudges to Kaushik about going to exercise, right? And I cannot expect that he will remember this nudge for very long. That's how the nature of these interventions are and how our behaviors evolve, right? So if I give a nudge, maybe he will remember for a few hours, but then something else, and I need to re-nudge again, right? So that's why these interventions have short-term effect, not long-term effect. There is no carryover effect, so to speak. So that's why we have to repeatedly randomize people again and again to assess the effects in a causal way. So this causal proximal effect estimation is a goal of this kind of trial. They based on scientific theory, the proximal outcomes, like the step counts that the participant will take, how much they are working, that are expected to eventually impact the distal outcomes of clinical interest, like diabetes status or depression, etc., the things that we ultimately care about, that is expected through the scientific pathway, biological pathway, but that's not part of the statistical design or optimization, so to speak. Right? This is something to keep in mind. Here is our first example. This is drink-less micro-randomized trial from the UK. This is, as the name suggests, this is about reducing alcohol consumption. And it's a 30-day trial. So there are 30 time points, T. Then we have different kinds of variables. We call it context, but these are basically covariates. In this literature, it's called context, but basically covariates X, then intervention A, and then the proximal outcome of interest, that is Y. In this case, the intervention is very simple. It's not even a factorial structure. It's a simple binary sending or not sending the nudge. Very simple structure there. But proximal outcome is here of interest is the engagement with the app, which is measured by the number of screen views the person has in the hour following the notification, that is 8 p.m. to 9 p.m. And this is what the psychologists, behavioral scientists, they figured out that this is the most vulnerable time for people to get into drinking. So let's intervene at that point. And of course, the distal outcome is the actual alcohol consumption, whether there is reduction or not. For those of you who are interested in a quick review, more or less non-technical review, so you can look at this paper we wrote at the American Journal of Public Health a couple of years back. And subsequently, I also participated in a podcast hosted by them, and this is available on YouTube. Okay, so that's basically the intro, and then I'll move to slightly more complex settings, but hopefully you got the basic grounding. So with the basic micro-randomization, from there I'll move to so-called adaptive micro-randomization, and in that context, I'll talk about this another trial, a little bit more complex trial called Diamante. So far, so good? Okay, so this is the trial. This is from California, specifically from the San Francisco Bay Area. From there, the two investigators, these are behavioral scientists, Adrian and Courtney, they had this app called Diamante, which is an acronym for Diabetes and Mental Health Adaptive Notification Tracking and Evaluation. So through a common friend, Joseph, they reached out to me, and then we got together to run this trial. So the goal was quite ambitious here compared to the other trial I mentioned earlier. Here, the goal is to develop, implement, and evaluate an adaptively learning mHealth intervention targeting physical activity to manage comorbid diabetes and depression. That means people who have both these conditions, right? And this is in the San Francisco area. So more specifically, if we untangle that, the statement, so one goal is to send contextually tailored text messages to people who are sick with these two conditions. And these interventions are already multifactorial, multi-component intervention. In a way, the randomization probability with which people are allocated to the different interventions keeps changing over time. So that's what we call adaptive micro-randomization. And the motivation behind this is to have increased ethics here, to take care of the participants. Because otherwise, if we do not deploy it upfront, then the trial participants do not get the benefit of the knowledge that we get out of the trial. Only the future people after the trial get the benefit. So that's why this adaptive trial design is introduced. Now,
We are sorry. I think we lost Bibhas. Bibhas?
yeah, I'm back again.
Yeah.
Sorry, I'm just getting disconnected. Okay, so. Oops. Um, We have to deal with the internet issues. Okay.
Yeah, the screen is
Okay.
visible, right?
Visible now. Okay, all
Yeah.
right, good. So, so I was talking about here, right? So in the classical drug trials, the adaptive randomization has been out there for many years, but that is just a static treatment, one drug given, followed for a while, but the drugs do not keep changing. Allocation to the people who get recruited, that changes over time. But here it's not just that. Here the people also get re-randomized to newer interventions. So it is a little bit different, a little bit more complex, a little bit longitudinal in nature. And this is where the reinforcement learning can help make a difference. This is our protocol paper, the clinical paper where we talk about this. So a little bit more about the trial design itself. It has two layers. One is a macro layer of the design, and another is a micro layer. So at the macro level, this is just a 3-arm RCT, right? So one arm is the random messaging arm, other one is the adaptive messaging arm, and the third one is control arm. But within each arm, there is micro-randomization. For the first two, for the random messaging arm, they get daily intervention messages micro-randomized. And for the adaptive messaging arm, they get daily intervention messages, but not evenly micro-randomized. They get this by reinforcement learning. So here, the algorithm itself learns which messages are working better for which people, and accordingly, it allocates the messages. And then the third one, the control one, daily messages, only some very low frequency updates. And this happens for 6 months, almost. Okay, so this is, again, just to clarify what the people are getting. People are getting on their screen 2 different messages every day. Right? One is a motivational message, other is a feedback message. As you see, there are 2 screenshots on from their phone. One message is feedback like, oh, yesterday you worked less than your goal. So, it just keeps reminding you about goal and how many steps.
We are having a connection problem. Back.
Okay, back. I have to do it again and again, it looks like. I don't know what's happening with my internet. Okay, so the motivational messages. This is the first factor. It has 4 categories, including one no message category. But there are different aspects of motivation. That's what is given. And these messages, these behavioral scientists, psychologists, they played around with it, they researched on it, they have even done evaluation, preliminary evaluation on the Amazon Mechanical Turk crowdsourcing platform prior to the main study. Likewise, there's this second factor, feedback messages. It has 5 categories, including no message. And then the third factor is time in the day, when you are giving the message, whether that has an impact, right? There are also 4 categories. So if you combine them together, this Diamante intervention involves a 4x5x4 mixed factorial structure. It's not that even, 2 to the power k or 3 to the power k, not that structure, but it's a mixed factorial structure. And then there are these many different contextual variables, covariates. There are a variety of baseline covariates and also time varying covariates, like the day of the week or day of study, like how long they have been in the study, or whether it's a weekday or weekend, because we are talking about lifestyle intervention. So all these factors have implication for how they behave, how they react to messages. And the outcome here is the number of steps in the next 24 hours following the message, And this is passively collected from various apps in the phone. This is our primary analysis paper that has been out. And I just want to highlight the key result from there. This is not an analysis of micro-randomization and all that. You can forget about it for a moment. This is a traditional analysis at the macro level. That means we have a 3-arm RCT, and we are comparing. This is a linear mixed effects model analysis. And as you see, visually, I'm not showing any numbers, any p-values, but this is a significantly different trend that we have seen. This black line, which is for the adaptive arm, which is basically the reinforcement learning employed there, we are seeing an improvement in people's step count as the time progresses, which is good news, which means the reinforcement learning is working there, right? I have not told you yet what is reinforcement learning. This is first advertisement that, okay, this works in this real trial. So let's now go back and see what we did, right? Okay, so that motivates us to study a little bit about what the reinforcement learning is and why it might be helpful. Finally, some notations. I'm sure many of you have been dying to see some notations. Otherwise, I've been just telling stories. So this is a little bit more than standard longitudinal data. And as you see here, the data structure involves X, A, and Y, 3 kinds of variable intertwined over time from 1 to capital T. X is the context or pre-treatment variable, A is the action, treatment, intervention, whatever you call it. And then Y is the proximal outcome or response or reward, different terms. And this A, the intervention, this can be a vector if there are multifactorial intervention, as in our trial. And X can also be high dimensional. So reinforcement learning is a pretty old area of AI, and this has been out there much earlier, before all this present hype around AI. This is an area that involves learning to take better actions. In our case, this is intervention or treatment, but in general, any action, any decision in an environment by interacting with it, by an agent. And the classical applications include robotics, automated flights, games, etc., etc. There's an excellent book by Sutton and Bartow that is a very good textbook for this area from a very computer science perspective. So visually, as you see, the learning agent takes action, interacts with the environment, and the environment gives the the outcome, and also provides a new state or new situation, context, covariate, whatever you call it. That's how it keeps learning. So this is our overall setting, broad sense. We have
Yeah. Again, I think probably lost.
Yeah.
So Bibhas, yeah, I see you. Can you then stop your video, maybe, and then?
Oh, okay. Yeah, I can stop the video and see how if that goes. Okay. Okay. You can see the screen, right?
Yes. Okay. Screen is visible.
Yeah. Okay. Okay. Good. All right. So this is our recent article on how this can be useful. Reinforcement learning can be useful in our biostatistics setting. And reinforcement learning is a broad area. There are different kinds of algorithm, but again, we have to zoom into a subclass called contextual-bandit algorithm or contextual multi-armed bandit algorithms. They provide an ideal framework for customizing GTIs or adaptive learning within an MRT that we are primarily interested in. But this is not just us looking into this area. This area, it has a long history, and then for a while it was forgotten, but then again revamped in the in the online advertisement industry. So, companies like Google and Facebook, and they all in the back end, they use some kind of contextual bandit algorithms to push the ads to the people, depending on their context, depending on their behavior. So from their point of view, the intervention is the advertisement that they are pushing to our page, right? And we are kind of the recipient of it. So instead, here we are doing it in the health setting. We are sending them nudges. These are the interventions. These are like the ads. But the patient covariates, all we collect is analogous to the online behavior in case of this online advertisement setting. So it's very comparable, so to speak. The algorithms are very suitable for both these problems. Now, one can talk about many aspects of this, but a central theme here is this so-called exploration, exploitation dilemma. And this is a dilemma that these algorithms face about whether to select interventions or actions with the highest expected proximal outcomes or rewards based on current estimates that are available to the algorithm, or to explore other situations, other interventions that may improve the estimates of the expected proximal outcomes. Remember, this is an online learning algorithm we are talking about. It's not, we are in classical statistics, what we are used to is the offline learning, where we have already collected the data. And now we are doing modeling, we are analyzing the data and finding out results. But here we have to interact with the system to generate data in the first place, right? So we must take actions, but should we take actions according to the best, according to the estimates, whichever action is looking the best, most promising? Should we trust that? Should we be greedy with our current estimates, or should we explore a bit more to collect more data, to explore other regions of the action space, so that eventually we get better? So it's a dilemma that algorithms face.
Can you increase your the screen size? I think full screen or
Okay.
Okay.
No,
still
better?
smaller.
Still large?
Yeah,
Okay,
on
so
the right side, bookmark.
Okay, good. All right. Is better now? Yeah. Okay. All right. So in particular, there is one algorithm called Thompson sampling that is quite popular nowadays. And this is actually a very old idea. As you see, 1933 Biometrica is about posterior sampling. It's a Bayesian method. The key ideas are that you specify a reward or outcome model, and then specify prior distributions for the model parameters like regression parameters. And then at every step, every stage of decision making, so to speak, you compute a posterior distribution of the parameters based on observed data so far, and select the action that maximizes the expected posterior reward at the given context. And then you have to generate corresponding reward data, because this is first you have to choose an action according to this method. Then you have to generate the data, outcome data. Then you have to repeat the steps again, and you have to keep updating the posterior. So there are, again, many versions, many algorithms, but the most common version is the so-called linear Thompson sampling, or LIN-TS. Came out in ICML in 2013. This is suitable for continuous updating every 24 hours, every day. Okay, so this is, I would say, this is a successful implementation of an existing idea, but then we want to do a bit more new stuff related to this, and that's the next section about Thompson sampling for zero inflated and over dispersed count data. So I go back to that trial I mentioned in the beginning, the UK trial, drink less. This is just to recap everything you have seen before. So the question here is that, can we redesign the drinkless trial as an adaptive MRT like the Diamante? So the Diamante trial was an adaptive MRT.
Did we lose him again?
You can share the screen again. Yeah, the screen is not visible now. Yeah.
Okay, give me a moment. Okay.
Yeah, please.
I don't know what's happening today, but yeah. So I cross this. It's okay now, right?
Yes, it is. Yeah.
Yeah.
But we can also, yeah. It's possible to increase the size of this entire screen that you were saying.
Yeah. Okay.
Right. Yeah, now it's perfect.
Yeah.
Yes.
Okay, good. So let's go to this section. So as I was saying,
Yes.
we recap this micro-randomized trial from UK, Drink Less, right? So this is this was not done like Diamante. No reinforcement learning was employed there. This was a purely micro-randomized, evenly micro-randomized. But the question that we are now looking at is, can you redesign this study to make it from this trial? This is extremely zero inflated, because look at the, if we go back and look at the outcome is engagement with the app measured by the number of screen views, right? So it's a small count, and often it can be zero. A lot of people are not even looking at the screen. So that's what this data is showing, a huge zero inflation and then small numbers everywhere else. And when we looked at the literature for the bandit algorithms, we didn't see much for potentially zero inflated and over dispersed count outcomes. So we wanted to address this gap. So these are the common count data models that you are all familiar with: Poisson, negative binomial, and the two zero inflated versions corresponding to these two distributions. However, one thing to note here is that the negative binomial with unknown dispersion parameter R, as well as the zero inflated models, they do not belong to the generalized linear model family, GLM family. So that has some implication, as you will see very soon. So when we wanted to employ Thompson sampling for the count data, we face some challenges. And then the challenges are that the posterior derived from the likelihood functions of count data models, that are standard count data models, and normal prior, which is usually used, because of the lack of conjugacy, the posterior becomes intractable. So in the normal case, in the normal Bayesian analysis, when we have lack of conjugacy, people often take recourse to Markov chain Monte Carlo methods for approximate sampling. But here, that's also challenging in the sense that this is extremely time consuming in an online setting. So in the classical statistics, the MCMC is okay because we just do one analysis, offline analysis. Data has already been collected and we just do a final analysis in the end. But here, we have to keep doing it again and again because this is online learning. Every time you have to fit a model, you have to draw. Thompson sampling goes on for as long as the T. So in the Diamante trial, for example, it happens every day over 6 months. So that's time consuming, right? So is there a simpler solution? So that's what we wanted to look at. And so we found this remedy in so-called Laplace approximation, where the idea is to, instead of sampling from the intractable priors, we simply sample the posterior samples are from a normal distribution with mean as the online MLE at time t and variance as a function of the online Fisher information at time t. And there is also some justifications, theoretical justifications from the literature, which says that in the Thompson sampling context alone, not talking about any other analysis, but in the Thompson sampling context alone, any
Bibhas?
I think.
Yeah.
Hmm. The slide is up. Yeah.
Slide is up. Okay.
Hmm.
Give me a minute. Okay, I was here. So I was
Yes.
saying that, yeah, this is good, right? Okay, so the justification for using this Laplace approximation is that any distribution for posterior that permits the Thompson sampling to explore far enough from the MLE, but not too much, that can theoretically guarantee good performance of the algorithm. And I'll come back to the aspect of the good performance, what it really means in a minute. And technically, these, far enough versus not too much, these things are, exactly defined. These are called anti-concentration property and concentration property. But I will not go into the technicalities, but it just gives a guarantee that as long as those things are satisfied, we can get good performance. That's the justification. So we have this paper currently under review at the Annals of Applied Statistics, also available from arXiv and associated R package, count TS. You can look it up. So with that idea, these are just the details of the algorithm. Without zero inflation, if in a particular data set you do not expect zero inflation, then this would be the algorithm. The key idea is that posterior sampling, everything is just additional details. I'll not go into this. This is suitable for count data that follow Poisson or negative binomial, if you know a priori. And then this is the other version, which is with zero inflation. Here again, additional details, but the ones highlighted in blue, those two steps are the crucial ones, the posterior sampling. One is for the beta, same as before. And the other thing is the gamma. This is for the zero inflation parameter. So there is this concept called regret. This is crucial for contextual-bandit algorithms. Regret in plain English, we understand that, oh, I wish I could do better, like the oracle, etc. So that's what is quantified mathematically. Formally, it is the expected difference in outcomes between the oracle and any candidate algorithm. So that's what is written here. This is a cumulative quantity. There is one frequentist version and one Bayesian version. Frequentist regret is that regret difference in expectation for a fixed true value of the parameter eta star. Whereas in the Bayesian regret, this is further averaged out over the prior distribution of the eta star. Bayesian regret is an average quantity, but frequentist regret is for any fixed quantity. So ultimately, this frequentist regret is useful, as you will see, because that kind of guarantees like a worst case scenario, as you will see. So every subdiscipline has its own culture. In this bandit algorithm, the culture is to bound the regrets. Whenever someone has to propose a new algorithm, the expectation is that they will bound the regret of that algorithm. And that's what we tried to do. So now regret bounds for Thompson sampling with GLM family of distributions, not just the linear, not just the normal, but in general, GLM family of distribution, including the Poisson distribution that already exist. However, I mentioned earlier that negative binomial with unknown dispersion parameter, as well as the two zero-inflated models, zero-inflated Poisson and zero-inflated negative binomial, they do not belong to the GLM family. So the existing results do not support this. However, as we have seen in our trial, this is highly zero-inflated data in the drinkless micro-randomized. So our theoretical contribution is to show that under standard conditions like bounded rewards and feature space, etc., I'm not showing those details, but the bottom line is that we have found both Bayesian regret bound and frequentist regret bound that match with the existing regret bounds for generalized linear model family distributions for Thompson sampling. Even though in our case, we have models, count data models that do not belong to the GLM family. However, as long as Thompson sampling is concerned, we are not missing much. We are not missing out. The regret bounds are same, right? And frequentist regret bound is the most useful one because it guarantees that this will happen for any true fixed value. So that means it's a guarantee for the worst case situation, whereas Bayesian regret bound only says on average this is where it is, but it may not be so useful for any particular unknown value. Okay, so with that, I show you some simulation results. This is all frequentist regret, and here true data generative model is over dispersed Poisson. And what are you seeing, right? The x-axis is the time or stage of the decision making, right? As time progresses, and on the y-axis it's regret, and regret is a cumulative quantity, so it cannot go down. It can become, at best it can become flat, right? It cannot go down. So our goal is to flatten the regret curve. Lower the regret, better the algorithm. That's the idea, right? So as time progresses, if we are effectively learning, then our regret curves must flatten up, must become more and more horizontal. It cannot be very steep. So that's the thing that we have to keep in mind. Then you look at the graphs, and these are the different panels are for varying degrees of over dispersion. But what we see here is that red line, the red curve with the yellow band, that is for linear Thompson sampling. That is the existing methodology that we employed in the Diamante trial. This is suitable for continuous data. But that's not suitable here, right, for count data. So clearly the count data models are doing better. And also to have an even playing field, actually following the suggestion of a reviewer of our paper. So we have already log transformed the data and then applied linear Thompson sampling to make it giving some kind of fairness to the comparison. Upper panels you are seeing, they are more or less same, all the count models, but you see some separation in the lower panel where over dispersion hits. And in general, I would say Poisson model is doing pretty good. Now, next slide. Here, the true data generative model has also zero inflation, not just over dispersion, but also zero inflation. And so what are we seeing? We are seeing as expected, the results. So not just the linear Thompson sampling doing badly, but also the models that do not address zero inflation, they are also not performing well. But the models that explicitly accommodate zero inflation, like the TS-ZINB and TS-ZIP, they are doing well. So that's what we see here. And finally, we do a comparison with MCMC-based Thompson sampling just for the sake of it, again, at the request of a reviewer in terms of why are we doing this approximate, this Laplace approximation thing as opposed to MCMC? So we see on the right side, we are seeing the regret curves. So the dotted ones are MCMC version, and the solid lines are the ones we proposed originally. So there is not much difference in the corresponding models between the MCMC approach and our proposed Laplace approximation approach. So regret-wise, while we are not losing much, whereas if you look at the left panel, we see a tremendous difference in computational time between MCMC and the Laplace approximation, which speaks favorably for the Laplace approximation. Okay, so we have done some additional simulation on top of the drinkless data structure using that data. Basically, we are redesigning that trial using that population's data. So we also keep here the static or non-adaptive version of the MRT that was actually done in practice. This is the brown kind of one that is the worst performance there, right? There is no learning, it's just randomization. But the rest are all we have seen earlier. Now the red line with yellow band, that is the linear Thompson sampling. On the left panel, we are seeing that initially that is doing pretty okay, pretty good actually, better than some count models. But then as T progresses, T increases, the count models are dominating over the linear Thompson sampling. And the model, I think the interpretation is understandable here because when there is little data initially, then the complex models may not be fitting very well. Then the linear Thompson sampling is doing better. But as we have enough data, as we have progressed a bit in the trial, then we can trust the count data models a bit. So that's the finding that we have seen from the application to the real data. So with that, I'll move to the discussion. Just a few take-home messages. The micro-randomized trials are new trials in the mHealth space that can be made adaptive, like the traditional drug trials also can be made adaptive by Thompson sampling or other reinforcement learning algorithms, thereby improving the trial participants' outcome, which is very ethical consideration. And we have new methodologies and software available for zero inflated count data, in addition to continuous and binary data that have been out there for a while. And one lesson that we have learned is that complex models like a negative binomial or its zero inflated versions, having mechanisms to accommodate over dispersion, may not necessarily outperform simpler models like Poisson and zero inflated Poisson in online learning setting. I think many of the things are different compared to our traditional understanding of things in an offline learning setting, which is the classical statistics. Whereas in this online learning setting, certain things are different. That is what we have learned here. And because of the repeated nature and the early on limited data availability, these things are playing a role here in behind these findings. Related work, this is causal inference. This is on the same data. We have developed some causal inference methods for this mobile health data. In fact, zero inflated count data with that UK trial in mind. We have analyzed the data, but that's for another day. We don't have time for that. I just wanted to highlight that these two things go hand in hand. One is the design of the algorithm to collect better data, and then other thing is how do we make causal inference out of that data. Future work, there can be a few that I can envision. One is the inference from this adaptively randomized data based on Thompson sampling. I just showed you the causal inference paper, but that's not for adaptively randomized micro-randomized trial. That's for fixed micro-randomized trial. It's not known yet, not fully understood, how the adaptively randomized micro-randomized trial would lead to causal inference. What are the implications for causal inference in that case? How is the performance affected? We are not too sure yet. And also, how do we learn across many users, borrowing information across users to increase efficiency in learning? That is another sort of open topic. Is because in the computer science literature, when people talk about contextual bandit, they treat the problem as if there is just one user, and you keep learning. And even the asymptotics for these kind of algorithms, the asymptotics happens over time. As t goes to infinity, what happens? But no one talks about n, combining across n, right? Which is the backbone of our statistical theory, that we have many people and we combine across them. So ideally, these two aspects need to be combined together to borrow information to increase efficiency. That is still in its infancy, I would say. So these are the more methodological things. And on the translational sides, I've been collaborating with various investigators in Singapore, UK, Australia, USA. And in fact, I would love to do one in India if I get the right partnership, some clinical investigators. So if you have contacts, feel free to connect to me. Thank you very much. I think that's all I have.
Yeah. Okay. Thank you, Professor Chakraborty. This is such a nice talk on this sophisticated methodology on this modern kind of mobile health data. So we have some time to take a few questions. So I'm moving to the chat Q&A. The first question is, and can you see the chat box, or should I read it? Okay, let me read it first. Yeah.
Yeah, please.
Yeah. For Bayesian regret, does the bound result hold under any choice of the prior? So for the yeah.
Okay, let me see. Go back. Bayesian. Yeah, no, we did not look at any prior. It is for it's basically normal prior. Prior is normal. Prior is normal, but the data model, the outcome model is that we vary across those 4 models for count data. We do not play with the prior.
Okay, this was the question from Arunangshu বিশ্বাস from GSK. Okay. Do we have other question? Okay, maybe people are writing their question. Let's wait for a few seconds. So I have a very small question here. So if let's say if we are following in this mobile health data also, sometimes we may not able to capture the total lifetime. What I wanted to mean is that if we lost someone from the trial, and but we have some partial data, then how can we kind of incorporate that partial data in the model?
So if you have partial data, but this is online learnings, right? So though at least what I'm looking at is online learning. So you keep following the person as long as you can till then, and then that's where it ends for that person, right?
Oh, okay. So
but if you are thinking about combining across these different people, which I think is ultimately very useful, and we are not there yet, then I don't know, maybe ultimately these are longitudinal data. So if you are analyzing so some kind of mixed effects models or GE, those kind of things you can think along, but then again, causal inference sometimes is problematic. So you have to look at more cutting edge, more sophisticated methods, not just the plain old GE or plain old linear mixed effects models.
Okay.
Problem.
Okay, I think we are on top of the hour, and I don't see also any questions. So I would like to thank Bibhas for this wonderful and very relevant presentation, and also to Kaushik to moderate it, and also to the people who are online. yeah, even though we had a little bit of like hiccup because of the internet, and we want to apologize, but it is nobody's hand. It was, just like happened. But we will be sharing the slides and also the recording with you guys, like, on LinkedIn page. So please stay tuned. And we will be again seeing you guys next month or month after. So saying that, have a great day. Bye, everyone. And thanks a lot, Bibhas.
Yeah, thank you.
Yeah.
Thank you for hosting. Thank you so
Yeah.
much.
Thank you,
Thank
Bibhas.
you. Bye.
Bye.
Yeah, thank you, everyone. Bye.